Hello everyone, I'm Mr. McBrien. This is SCH3U, molar ratios, and the Slingshot. The Ontario curriculum states that students will explain the quantitative relationships expressed in a balanced chemical equation, and that will calculate the corresponding mass or quantity in moles and molecules for any given reactant or product in a balanced chemical equation. Today we're going to move from working on the building blocks to doing some of these calculations in anger. So we're going to learn how to use a balanced equation to calculate the amount of reagents needed and the amount of product that will be produced in a given reaction. Establish how to use a given question that's asked in a test or an assignment or one posed by a scientist to determine the stoichiometric term, the stoichiometry term. And then we're going to learn how to use the stoichiometry term in a tool called the Slingshot for calculating masses of reactants and products and reactions. Okay, so we've got a busy one today, so let's move right along. Quick definition. Stoichiometry is the study of the quantitative relationships among the amounts of reactants used and the amounts of products formed in a chemical reaction. Now that's just a way of saying that while we measure and communicate the amounts of chemicals or compounds in terms of mass, compounds communicate with each other in terms of moles. And by communicate, we generally mean react. So they think in moles, and we need to too in order to understand how they react with each other. And so what we're going to do is relate the number of moles of compounds to each other using molar ratios. And in our class, we're going to use a very specific, carefully designed version of the molar ratio, and this is going to dramatically increase our success rate when we're doing calculations. So it's probably as easy as anything for us to just simply illustrate this with a standard reaction. And the Haber process is very famous, and you've probably already seen it before. It's a process by which we can artificially, using man-made tools, fix nitrogen. Something that is done quite handily in nature, but without it, really we'd probably have chopped down every tree on the planet in order to feed ourselves. But because we found a way to fix nitrogen ourselves, we can make fertilizer very effectively and make our land much more productive. Okay, enough about that. Let's say we were setting up a reactor to fix nitrogen, and we wanted to figure out how many moles of hydrogen gas we needed to add to the reactor for every mole of nitrogen that we put in. Well, our balanced equation pretty much gives us the answer by examination. So for every 1 mole of nitrogen, notice that the 1 is implied here, we need 3 moles of hydrogen gas, straight out of our balanced equation. Now, so the answer isn't that difficult to get, 3 moles of hydrogen per mole of nitrogen. Okay, let's try another one. How many moles of ammonia can we expect per mole of hydrogen gas we put in? Well, we can see that we can expect 2 moles of ammonia for every 3 moles of hydrogen gas. 2 moles of ammonia for 3 moles of hydrogen gas. And we can simplify that to say 0.67 moles of ammonia per mole of hydrogen. And this is stoichiometry. Okay, let's look at another example. The Apollo lander got up and down from the moon using hydrazine fuel. So, for anybody who's keeping track, this is rocket science. We have hydrazine reacting with nitrogen tetroxide to form nitrogen gas and water. Okay, let's ask ourselves a question. If we're loading up the Apollo lander with fuel, how many moles of hydrazine do we need to put in for every mole of dinitrogen tetroxide? Well, we can see that the 1 is here implied. So we can say for every 1 mole of dinitrogen tetroxide, we need 2 moles of hydrazine. 2 moles of hydrazine per mole of dinitrogen tetroxide. Okay, now let's think in terms of products. How many moles of nitrogen do you get per mole of hydrazine? Well, we get 3 moles of nitrogen gas for every 2 moles of hydrazine. And 3 for every 2, we can again simplify to get 1.5 moles of nitrogen for every mole of hydrazine. Okay. These ratios are in fact stoichiometry, and we can do a slight tweak to this to create a stoichiometric term that will be correct every single time we want to do the reaction or do the calculations that we're going to talk about coming up soon. So here's a few tips for successful extraction of the stoichiometric term. It's really pretty easy to get this term right and get our first mark on the reaction question before we even really have to think. So the first step, confirm that the equation is balanced. If it's not balanced, it needs to be balanced. Otherwise, you're going to get the stoichiometry term incorrect. The next step, determine the components of interest. Okay, what you need to do is determine the component that you know, the one that you've been given, and determine the component that they're asking for. And once you've done that, it's easy to get the stoichiometry term correct. What you do is you write the thing you want on the top and the thing that you're given on the bottom and just make a fraction. And once you do this, and if you record the information in the stoichiometry term the way we're going to show you, you can verify your units as you complete the calculation and always, always get the correct answer. Okay, so let's take an example. The question is, we burn 3 grams of this compound. How much CO2 will we get? Well, we need the balanced equation, of course. And once we have the balanced equation, then we figure out what we know. In other words, what we've been given. We were given the amount of this compound. And we figure out the thing they're asking for, how much CO2 we're going to get. And this gives us what we need to create our stoichiometry term. All we have to do from there is simply take the coefficients for each one, 12 for the CO2 that we need, and 1 for the carbohydrate, and we have our stoichiometry term. 12 moles of CO2 for every 1 mole of our combustible material. Okay, so let's try another example. The question is, how much copper sulfide do we get when we fully react 82 grams of copper? And we can quickly check to make sure our equation's balanced. And then what we want to do from there is figure out what we were given. In this case, we know that we have 82 grams of copper, so that's our given. And figure out what we need. So our given and our needed. Then we simply construct our stoichiometry term by putting the thing we need on the top with the coefficient from in front, and the thing we're given on the bottom, again with the coefficient in front. Okay, another stoichiometry term to define. How much HCl do we need to make 6 grams of magnesium chloride? Excuse me. Okay, so we're given magnesium chloride. We know that's going to go on the bottom. We need the HCl. We know that's going on the top. So we construct it with the needed on the top, the given on the bottom. And we know, as long as we apply this term correctly, we're not going to have any trouble. Okay, one more, and maybe a kind of trivial one. Excuse me. So, we have the reaction of calcium oxide with carbon dioxide. How much carbon dioxide do we need to fully react 7 grams of calcium oxide? Alright, our given is calcium oxide. We know we've got 7 grams of it. Our needed is the amount of CO2. And so we design our stoichiometry term, again, with the needed on top and the given on the bottom. Okay, so what I'd encourage you to do right now is pause the video and just practice the stoichiometry term using the limiting reactants worksheet. And question 1 is dedicated to stoichiometry terms. And again, don't try to solve the problem, just simply write the stoichiometry term. Once you're done, you'll have had some practice. And then you can return to the movie and watch the rest. Okay, welcome back. Hopefully now you've worked your way through the stoichiometry term questions on the limiting reagents worksheet, and you're a pro at relating numbers of molecules to numbers of molecules. Now what we'd like to do is apply these terms. So the stoichiometry term relates moles to moles, but we tend to measure and communicate amounts of compounds in mass. So the good news here is that we're experts now. We've spent over a week converting to and from masses, and we shouldn't have any problem being able to leverage these terms. Okay, and how do we actually use them? We're going to do 3 kinds of calculations, and these represent the main ones that we need to do when we apply stoichiometry. So the first one is illustrated by this question. I have 4.26 grams of reactant A and 7 grams of reactant B. How much product will I get? The second kind, I need 8 grams of product. How much of each of the reactants A and B do I need? And the final one, I have 6.34 grams of reactant A. How many grams of reactant B do I need to fully react them? Okay. We know how to build a stoichiometry term. Now what I'd like to do is introduce the slingshot. And it's just a tool for visualizing how to efficiently use our stoichiometry term to get the right answer every single time. Okay. So slingshot has 3 steps. We pull it back, we aim at the target, and then we release it forward. And our calculations today have 3 steps as well. we are going to find the number of given moles from the grams that are given in the question. We're going to relate those given moles to find the number of needed moles using the stoichiometry term. And then we're going to convert the moles to the needed grams and report that and collect full marks. Okay, so a little cartoon to help us get that idea through. So let's say we're given the mass of the reactants. I have 4.26 grams of reactant A and 7 grams of reactant B. How much product will I get? Well, we fire up our slingshot. The first thing we do is apply our molar mass to get the number of moles of each of the reactants. Next, we use our stoichiometry term to find the number of moles of products. Finally, we again apply our molar mass, this time of our products, to turn moles of products into mass of products. So it's a three-step process, and we know how to do all three of these steps. So that's question 1. The next question is when we're given the mass of products. So I need to make 8 grams of product. How much of reactants A and B do I need? And we do the exact same thing. First off, we calculate the number of moles of product. Then we apply our stoichiometry term to get the moles of reactants. And finally, we again apply the molar mass, this time of the reactants, to get the mass of the reactants that we're going to weigh into our reaction flask. And finally, the last approach is when we're given 6 grams of reactant A and we're asked how many grams of reactant B should we measure into the reaction flask to fully react reactant A. And of course the process is again very, very similar. We find the number of moles of reactant A by using the molar mass. We apply the stoichiometry term to find the moles of reactant B. And then we use the molar mass of reactant B to calculate the mass of reactant B and report it out and collect 100%. Okay, so now let's pull it all together, looking again at our familiar Haber process. How many grams of hydrogen gas do we need to fully react 1 gram of nitrogen? Okay, so first off we'll build our stoichiometry term. And again, the thing we need goes on the top. It asks us for how many grams of hydrogen gas. So we put it on the top, pulling the coefficient from in front of hydrogen. So we need 3 moles of hydrogen for every 1 mole of nitrogen. So the next thing we do is find the number of moles of nitrogen. And that's very straightforward. 1 gram of nitrogen equals 1 gram divided by 28 grams per mole. Remember, that's just the molar mass of nitrogen. And so we can say that we have 0.0357 moles of nitrogen. We can then apply our stoichiometry term to find the number of moles of hydrogen. So we simply multiply the moles of nitrogen times our stoichiometry term. And notice how useful our units are in this case, because moles of N2 cancels out if we carry it through. So we multiply by 3 moles of hydrogen for every mole of nitrogen, and moles of nitrogen cancels out and we're left with moles of hydrogen. Finally, the third step in the slingshot, we multiply by the molar mass of hydrogen, and this gives us the number of grams of hydrogen that we need per gram of nitrogen. And if we wanted to wrap this up, we would say we need 0.216 grams of hydrogen for every 1 gram of nitrogen. Okay, we'll do another example. We react 1 gram of nitrogen. How many grams of ammonia do we get? Okay, first off, we'll make the stoichiometry term. So the thing we need is ammonia. The thing we are given is nitrogen. We pull the coefficient from ammonia and say we get 2 moles of ammonia for every 1 mole of nitrogen that we put in. Next, we need to move the 1 gram of nitrogen into the molar domain, and we do it here. We multiply by the stoichiometry term, again canceling moles of nitrogen, but in this case, what we'll retain is moles of ammonia. So 0.0357 moles of nitrogen times 2 moles of ammonia for every 1 mole of nitrogen gives us 0.0714 moles of ammonia. And of course, we're asked for grams of ammonia, so we need to convert back using the molar mass of ammonia. So we multiply 17 grams per mole times 0.0714 moles equals 1.22 grams of ammonia. So if we react 1 gram of nitrogen, we will get 1.22 grams of ammonia. Back to rocket science. How many grams of hydrazine should we put in the reactor if we put in 2 grams of dinitrogen tetroxide? Okay, first we'll build our stoichiometry term. The thing we need on the top, 2 moles of hydrazine, and the thing we are given on the bottom, dinitrogen tetroxide. Pull the coefficients from the balanced equation. Next, we need to find the number of moles of dinitrogen tetroxide. So we know we started with 2 grams. Divide by the molar mass. Grams cancel and moles go up on top. 0.0218 moles of dinitrogen tetroxide. The center of the slingshot means we need to multiply by the stoichiometry term. So, 2 moles of hydrazine for every 1 mole of dinitrogen tetroxide times the number of moles of dinitrogen tetroxide. Notice that moles of dinitrogen tetroxide cancels and we're left with moles of hydrazine. So, we need 0.0436 moles of hydrazine. But, again, we can't weigh moles on a balance, so we need to convert to grams, and we do that by multiplying by the molar mass. And moles cancels out, and this gives us 1.39 grams. Okay, so we have the tools that we need, but many chemists prefer to do this rather than doing it stepwise. Many prefer to actually combine all 3 steps and solve for this target amount in one large equation. So we're going to cover that briefly here. If you think about it, it's the exact same process. And I'm going to try to illustrate that by showing the slingshot one more time. Okay, so our example, finding the mass of the product, in this case, given the mass of the reactants. So, in my magnesium with acid reaction, if I react 5 grams of HCl fully, how much hydrogen gas will I get? So let's fire up the slingshot. First off, we're going to calculate the number of moles of reactants. So let's just put a term in here for mass of our reactants divided by the molar mass of the reactants. So this is just step 1 of the slingshot. Now let's apply the stoichiometry term. Number of moles of product divided by number of moles of reactant. So it's the number of moles of hydrogen for each mole of our reactants, HCl. Next, we need to move ourselves back into the mass domain, and we do this by multiplying by the molar mass of our product. So we can actually apply everything that we did in one great big equation, and we should get exactly the same answer. So let's go through it quickly. We have 5 grams of HCl, and we divide by the molar mass of HCl to get the number of moles of HCl. Then we multiply by our stoichiometry term to get the number of moles of hydrogen. Then we move ourselves back into the mass domain by multiplying by the molar mass of hydrogen. When we're finished, we get our answer. If we react 5 grams of HCl fully, we'll get 0.14 grams of hydrogen gas. Now, where's the benefit to taking this approach? Well, one of the most interesting ones is that we can visually cancel everything that we did. Notice that grams of HCl is over here on the left, and we divide over here. They cancel out. Notice that moles of HCl is on top here and on bottom here. Again, they cancel out. Notice that moles of hydrogen gas is on top here and on the bottom here and cancels out. What we're left with is simply grams of H2, which is exactly what we were asked for when we started. So this approach for using one big equation for the slingshot, in fact, is inherently checking our data as we go. It's up to you which approach you take. Each one is equally valid, but they each have their own advantages. So just see which one works for you. Okay, a few final tips then. Remember, we mentioned at the start, do a quick check to make sure the equation's balanced. If it's not, you need to balance it or your stoichiometric ratio will be incorrect. Next, remember the whole point of the slingshot is that stoichiometry only applies in the molar domain. So we can't relate masses to masses directly using the stoichiometric ratio, only moles to moles. And so you want to resist the temptation to apply those molar ratios to masses. You're going to get wrong answers if you try that. In the final note, as we mentioned before, don't limit significant figures with your stoichiometric coefficients. You can treat those as accurate a number as you need. Alright, you should have the tools you need now to complete the worksheet and go and do some reaction questions in anger. I know this was an in-depth concept. Please go ahead and read the chapter and see if you can cement these concepts, and then there are a few questions in the textbook that you can try to make sure that you've got it down perfectly. Thanks very much. Have a great night.